Welcome back. Today we're going to go through section 1.1 from the book, the first section of the book. This is a very fundamental section. The techniques we're going to go over here today, I would strongly suggest that you practice them, go through the examples in the book, go through some and solve some exercises out of the book. Make sure you have a good handle on what we do here today, because this is the foundation for a lot of what we're going to be doing for the next little while. So this course deals with linear equations. The first thing is, what is a linear equation? Well, a linear equation is an equation that looks something like this. What are the key aspects of this? Well, we have these things called coefficients. These are numbers. Normally they're real or complex numbers. We are only going to deal with real numbers, so they're numbers. The x's, and it could be x1, x2, x3, it could be x, y, z, it could be a, b, c. These are variables. Okay? So when you see an equation like this is called a linear equation. The key thing here is that your variables don't have squares, don't have square roots, they don't have exponentials, they don't have anything like that. They're just simple variables. So a linear equation looks something like 3x1 plus 4x2 minus 3x3 plus the square root of 41 times x4 equals 27 over 17. That's a linear equation. It's a number times a variable, plus or minus a number times a variable, plus or minus a number times a variable, and so on. Now, linear equations can be written a little bit differently, but the key thing is to note that it is just a number times a variable. So you could see it written something like 3x1 equals 2x4 minus 27 plus 9x3 plus x2. That's, again, a linear equation, because none of your variables are being squared or square rooted or doing anything to your variables. They are just a number times your variable. That is a linear equation. These are the things we're going to be dealing with. The next thing to look at is a system of linear equations. This is when you have a collection of linear equations, a whole bunch of them, that all have the same variables. Now, not every variable has to appear in every equation, but it has the same variables. So for instance, this is a system of linear equations. In this case, we say that this is a system of linear equations with three equations in three variables. We have three variables, three equations. Okay? That is a system of linear equations because the variables repeat throughout. Again, not every variable has to appear in every equation, but it's the same variables in the equations. We are going to be asking a lot to solve systems of linear equations. And the first major thing we're going to be seeing in this course is how to solve systems of linear equations. So, what is a solution to a system of linear equations? Well, a solution to a system of linear equations is a list of numbers that when you substitute them in for your variables, it makes everything true. So, for instance, I'm claiming that this system of linear equations has the solution 1, 3, 1. That means that if I take the number 1 and put it in for x1, take the number 3, replace x2 with 3, take the number 1, replace x3 with the number 1, everything is going to be true. So let's quickly see that that's true. Take our first equation and plug in those numbers. So 2 times x1 is 1, plus 3 times x2 is 3, plus 7 times x3 is 1. Well, that equals 2 plus 9 plus 7. Add 2 plus 9 plus 7, that equals 18. That's correct. That matches what I claimed. But my second equation, minus 2 times, well, x1 is 1, plus 2 times x3 is 1. What does that give me? Minus 2 plus 2 equals 0. That matches there. That's correct. And the third one's pretty easy to see. X2 is equal to 3. Okay, so those numbers, that gives me a solution to my system of linear equations. It's a set of numbers that works for all of the equations. Sometimes there's multiple solutions. In fact, sometimes there's infinitely many solutions. When we have the collection of all possible solutions, whether it be one or infinitely many or no solutions, we call that a solution set. So if we have a system of linear equations, gather all of the possible solutions up to that system, we call it the solution set. Two linear systems are called equivalent if their solution sets are the same. So let's see what this means. So here's a solution set example. In fact, you might recall that in the previous lecture, we saw this exact system of linear equations, and it was solved out using some of the techniques for solving systems of linear equations. We saw that this has a single solution. Well, let's double check this. Take the equations, take the first equation, 2 times x1, I'm claiming that x1 is equal to 4, plus 3 times x2, which I'm claiming x2 is equal to 1. Multiply them out, I get 8 plus 3, that equals 11. That checks out, that matches what I have up here. Now my second one, minus 2 times 4 plus 2 times x2 is 1 in the solution set. What does that give me? Minus 8 plus 3, plus 2. Minus 8 plus 2 is minus 6. That checks out. So this is a solution. This is, in this case, it is the only solution. We will be seeing how to tell when you only have one solution, when it's the only solution. But for now, just trust me that this is the only solution to this system of linear equations. Here's another set of linear equations, another system of linear equations. And I'm claiming that the solution to this is 4, 1. So let's plug that in and double check. So take my first equation, x1 plus 4 times x2. What does that give me? 4 plus 4. 4 plus 4 equals 8. That checks out. Let's look at the second set, or the second equation. 2 times x1 minus x2. That gives me 8 minus 1 equals 7. And again, that checks out. Okay, so this is a solution to the system of linear equations. In fact, it is the solution set because it's the only solution for it. But now take a look at those last two examples. That was the first example we saw. That was the second example we saw. Both of these had the solution set the exact same. Now, all of these equations are very different, but each of these systems of solutions, the two of them, have the same solution set. So we say that these two systems are equivalent. The solutions are the same. So equivalent just means that your solutions are the same. In fact, if you take these, one idea might be take all of these and graph them out. You'll see that all of the lines that are here, they're all different lines, but they all are going to intersect at the same point for 1. So that's an exercise. Graph these out and just confirm graphically, and you can see what's happening. So here's the first concept that one of the first concepts we're going to deal with: consistent and inconsistent. If a system of linear equations has a solution, at least one solution, it may have infinitely many, but if it has at least one solution, we say it is consistent. Sometimes you will end up with a system of linear equations that has no solution. When that happens, it is called inconsistent. And spoiler alert, here is one of the major results of systems of linear equations. That when you have a system of linear equations, you are going to have three possibilities. First possibility is no solution. That's an inconsistent set. The second possibility is exactly one solution. Or the third possibility is infinitely many solutions. There is no such thing as a system of linear equations that has exactly three solutions. It either has one solution or it has infinitely many solutions. There is nothing in the middle when it comes to systems of linear equations. So we are going to look more at this result in the future, but in fact, it's going to be one of the first major results that we see dealing with systems of linear equations, why this happens. No solution, that's inconsistent. If there's one solution or infinitely many solutions, that is consistent. Okay, now we are going to be dealing a lot with matrices. In fact, almost all of the solutions that we're seeing and the techniques we're going to be using, we are going to be using matrices. What is a matrix? A matrix is simply a rectangular array of numbers. That's a matrix. We can talk about the size of a matrix. A size of a matrix is the number of rows by the number of columns. So for instance, this matrix, you count the rows, it has 3 rows, count the columns, it has 2 columns, we say it is a 3 by 2 matrix. The second one over here, count the number of rows, 2 rows, count the number of columns, 3 columns, it is a 2 by 3 matrix. Always, always, always give the number of rows first. When you're talking about the size of a matrix, you always give the number of rows first. A 3 by 2 matrix is different from a 2 by 3 matrix. Okay? So this idea of the size of a matrix is the number of columns by the number of rows of the matrix. So let's pull these things together. We talked about systems of linear equations. What we are going to do is we are going to take the coefficients from a system of linear equations and put those in a matrix. After all, those are the important things. If you really start to get into it, you're going to see that the variables don't matter. The variables are just names that you give to them. And the idea is that you have the first variable, second variable, third variable, and so forth. But what you call them doesn't matter. You can call them x1, x2, x3. You can call them ABC. You can call them x, y, z. It doesn't really matter. The important thing are the numbers that are associated with it, the coefficients. So what we do is we take all those coefficients, we pull them out of the system of linear equations, and we put them into a matrix. So for instance, if we look at this system of linear equations, we have 3 variables. This is a system in 3 variables. Our 3 variables are x1, x2, and x3. What we are going to do is build the coefficient matrix. So for the coefficient matrix, what we do is we take one column for each of our variables. And we look at it and say, okay, x1, my first equation has x1 has a value of 1. So I put a 1. My second equation has a 2 for x1, so I put a 2. And working my way down, my third equation has 2x1, so I put a 2. Repeat it for the x2s. So my x2 is my second column. I have 3x2s in my first equation. I have 3x2s in my second equation. My third equation has no x2s, so it's 0. Now what about my x3s? Working down again, my first equation has 2. My second equation has -1. My third equation has -1. So I'm missing the negative on there. So this is called the coefficient matrix. But now that's not all my numbers. I also have these numbers on the right-hand side, my constants. Okay. So these constants on the right-hand side, I'll often put them in another column in my matrix. So you see, here are my coefficients. Here are my constants. When I do this, it's called an augmented matrix. My coefficients plus my constants in an extra column. So we will often take a system, we will almost always, in fact, take a system of linear equations that's given as equations and put it into matrix form to build our coefficient matrix and our augmented matrix. So let's see what we can do with this once we have this. Let's look at solving a system. So we've talked about, and you've seen in the past, hopefully, solving a system of linear equations, a small system, by using elimination. So the idea is that you start to get rid of variables one at a time. So I have this system of linear equations. Notice I have taken this system of linear equations and I have built the augmented matrix from it. So what are we going to do? To eliminate this, first off, I'm going to use my first equation to get rid of the x1 in my second equation. So how do I do this? Well, here's my first and second equation. Well, I noticed that the easiest way to do this is to have the same coefficient in front of the x1 in both of them. So how can I do that? Well, let's take my first equation and multiply the entire thing by 2. What am I going to get? 2x1 plus 6x2 plus 4x3 equals 26. I've just taken the entire equation, multiplied it by 2. We're allowed to do that. Now, my second equation, I already have the 2x1, so I'm just going to write that as 2x1 plus 3x2 minus x3 equals 5. Just rewrite it. So now I have the same coefficient in front of the x1s. I can subtract one equation from the other. And what happens? My x1s disappear. I get 6x2 minus 3x2 gives me 3x2. 4x3 minus negative x3 gives me plus 5x3 equals 26 minus 5 is 21. So I have used these two equations and gotten rid of one of my variables. Now I'm going to take this new equation and use it in place of the second equation to get rid of it. So that gives me this system. And now with this system, you can see I have an augmented matrix for that system as well. What I did was I eliminated a variable and I have a new augmented matrix. So let's do the same thing. Let's get rid of the x1 from that third equation using the first equation. Here's my first and third equations. I'm going to do the same thing. I want to get the same coefficient in front of the x1. Well, the easiest way to do that is to take my first equation, multiply it by 2. I get 2x1 plus 6x2 plus 4x3 equals 26. My second equation, I've already got the 2x1, so I get 2x1 plus x3 equals 5. Subtract again. What am I going to get? 6x2 plus 3x3 equals 21. Again, I'm eliminating that variable from the third equation, so that means I take my new equation and replace my third equation with that. And what do I get? Here is what I get, which gives me a new augmented matrix. So eliminating these variables one at a time is giving me a new augmented matrix every time. Let's follow through. Now I've gotten rid of the x1 every place but the first. I'm going to use the second equation now to get rid of the x2 from the third equation. Again, using the idea of the elimination. So let's do the same thing. I'm going to take my first equation, multiply it by 2, because I see if I double that, I will get the 6. So I get 6x2 plus 10x3 equals 42 by doubling my first equation. My second equation, I've already got the 6x2, so 6x2 plus 3x3 equals 21. I subtract one from the other, my x2's disappear, I end up with 7x3 equals 21. That now replaces my third equation, and I get this system, which has this augmented matrix. So by, again, eliminating something gives me a new augmented matrix. Now we can easily find the value for x3. We have a nice, easy little equation here. So 7x3 equals 21. That tells me that x3 is equal to 3. Here is the first variable solution. So now I have x3 equals 3. I can use that now to solve for x2 because I have that equation. So 3x2 plus 5x3. Well, I know that x3 is equal to 3 equals 21. 3x2 plus 15 equals 21. 3x2 equals 6. x2 equals 2. Now I know what my x2 is equal to. Let's plug it into my next one. I have x3 equals 3, x2 equals 2. I can use that first equation now to solve for x1. So x1 plus 3 times x2 is equal to 2, plus 2 times x3 is equal to 3, equals 13. Simplify it, solve it out. x1 plus 6 equals 13. That gives me x1 plus 12 equals 13, or x1 equals 1. There is my system, my third number. So I have the overall solution, x1 equals 1, x2 equals 2, x3 equals 3. And notice again that this is also a system of linear equations. So I can write that out as an augmented matrix. Now that I have the system, let's double check it, make sure it works. So take my first equation, plug in my solution. I get 1 plus 3 times 2 plus 2 times 3 equals 1 plus 6. That's 13. That checks out. Take my second one. 2 times x1 is equal to 1 plus 3 times x2 is equal to 2 minus x3 is 3. What is that? That is 2 plus 6 minus 3. Add those up. That's 8 minus 3 is 5. That checks out. My final equation, 2 times x1 is 1, minus x3 is 3. That gives me, oh sorry, that is a plus, not a minus. That gives me 2 plus 3 equals 5. That checks out. Sorry, I just wrote that down wrong. That gives me 5. So that works out. Always a good idea to check your work when you get the solutions, just to make sure that you didn't make a mistake. It's very easy to make an arithmetic error somewhere along the way. Always double check your work. So we have a solution to the system using elimination. And at each step along the way, I built an augmented matrix. Now, what we are going to be doing eventually is we are going to forget about the system of linear equations and we are just going to use the matrix. So go through this example, go through some of the other examples from the book. Make sure you understand how doing the elimination gives you a whole series of matrices. Now, take a look at the matrices that we just did. At each step along the way, we only did certain things to matrices. Okay? This is something we're going to call elementary row operations. We're going to get into a lot more of these, but these are things that you are going to be allowed to do to a matrix to try solve a system of linear equations. Okay? And we will be doing a lot more of these as time goes on. So there are only 3 things you're allowed to do. You can add a multiple. First off, add a multiple of one row to another row. So in this case, I look at the rows. I have 3 rows in my matrix. What I am doing is I am going to take row 2, double it, multiply every number in there by 2, add row 2, and this becomes my new row 2. So in this case, you take twice row 2, twice row 1 plus row 2. So 2 times 1 plus 2, that's 2 plus 1, that gives me 4. That's my new number here. 2 times 3 plus 1, that gives me 7. There's my new 7. 2 times 2 is 4, plus negative 1 gives me 3. That gives me my 3. So I have taken my row 1, multiplied every number in there by 2, added row 2 to it, and it gives me my new row 2. That is one of my elementary row operations. Another thing I'm going to be allowed to do is to interchange any 2 rows. So in this case, this is much simpler. I've just taken row 2 and row 3 and exchanged them. So you can see that row 2 has become row 3 has become row 2. I've just exchanged them. And the third thing I'm going to be allowed to do is to multiply every entry of some row by a number. So 3 row 2 is my new row 2. I've just taken my row 2, multiplied every number in there by 3, and I get this. Okay? These are called elementary row operations. We're going to be doing a lot of these, so you're going to get lots of practice. So this is just your first introduction to elementary row operations. This is the key to solving systems of linear equations. So we'll be going through these a lot more in the future. What we're going to do is we are going to do row operations one after the other. So we're going to do some row operations to an augmented matrix. We're going to do some more operations to what we come out with. We're going to do more row operations to what we come out with. We're going to have a whole series of matrices. Any 2 matrices that you do this to, if you start with a matrix, do some row operations, and come out with a new matrix, these are called row equivalent, if you can go from one to the other by doing row operations. These are equivalent matrices. So for instance, this matrix is row equivalent to this matrix. And if you go back to the previous example, you'll see that this is the matrix we started with that previous example. We did a whole bunch of eliminations. We got down to that matrix. An elimination is essentially a row operation. So we took that matrix and turned it into that matrix by doing eliminations, which is the same as doing row operations. So this again is another concept we're going to see a lot more of. One important thing to note is that elementary row operations are reversible. If you take a matrix, do some row operations to it, you turn it into a new matrix, you could do some row operations to that and turn it back into what you started with. So this is a concept that we're going to be dealing with. And here is one of the key results that we are going to be, that is kind of underlies everything that we're doing. An elementary row operation doesn't change a solution set. So we have a system of linear equations. We're looking for a solution. We turn it into a matrix. We perform elementary row operations. By doing those row operations, we do not change a solution set. So what we are going to do is, well, when you look at a system of linear equations, it's a whole bunch of numbers and variables all stuck together. You can't really tell what the solution is by looking at it usually. What we're going to do is we are going to turn into a matrix and do elementary row operations to the point where we can essentially just look at the matrix and read off the solutions. So for instance, with our earlier example, when we have this, we got down to that final matrix, we can turn that matrix back into a system of linear equations. Take that second matrix, what do we have? We have x1 plus 0x2 plus 0x3 equals 1. Take the second row, it's 0x1 plus x2 plus 0x3 equals 2. Take that third row, we get 0x1 plus 0x2 plus x3 equals 3. You can just read this off. x1 equals 1, x2 equals 2, x3 equals 3. The idea is to take something that looks complex, like our first matrix, where you know there's probably a solution in there, but you can't see it easily. We're going to perform a whole bunch of operations to turn it into something where I can say my solution is x1 equals 1, x2 equals 2, x3 equals 3, where I can just read off the solution. Okay, so we're looking for solutions. Elementary row operations give us a way of turning a system of linear equations into something where we can just read off the solution. That's the whole key of what we're doing. So here's an example. Let's solve this system of linear equations. Again, we're going to use elementary row operations here for this. So if I take this system of linear equations, first thing I do is I build my augmented matrix. So again, building the augmented matrix is getting rid of the variables and just pulling out the numbers. So I have my variables are x, y, and z, and then I'm going to save a column for my constants. So when I read down the equations, I'm going to build my augmented matrix by first looking at all the x's. I have 2, 1, 1. Now I look at my y's. I have 1, 3, and 1. I look at my z's, -1, 2, and -1. And my constants, 2, 1, 2. There is my augmented matrix. And this augmented matrix gives me what I need to start with and to solve my system of linear equations by using elementary row operations. So let's see what we can do here. Here's my augmented matrix. So what I'm going to do is I am going to perform a series of elementary row operations that is going to give me a matrix where I can just read off the solutions. The idea is to start looking at this and say, okay, how can I get rid of numbers here? Turn numbers into zeros. So first off, I'm going to note that in this first one, if I take my row 1 and I subtract twice row 2, I am going to take 2 minus, if I look at my x1 column, that is going to get rid of this number and turn into a 0. So I'm going to make this my new row 2. So what does this give me? Row 1, this tells me row 2 is the only one that's changing, so row 1 is going to stay the same. 2, 1, minus 1, and 2. Now for my row 2, this is what I'm changing. I'm going to say take row 2 minus twice row 1. So it's going to be 2 minus 2 times row 1, 2 times 1. My second number in here, I'm going to give myself a little more space here. Row 1 minus twice row 2. My third number is minus 1 minus twice what's in row 2. And then finally, row 1, which is the 2, minus twice times row 1. And my third row doesn't change. 1, 1, minus 1, and 2. What's that equal to? 2, 1, minus 1, 2. My second row becomes 2 minus 2 is 0. 1 minus 6 is minus 5. Minus 1 minus 4 is minus 5. And 2 minus 2 is 0. And my third row stays the same. So with an elementary row operation, I have taken my starting matrix and turned it into that matrix. That is an elementary row operation. So now I'm just going to recopy that matrix down here, just to give myself a little more room. Now, if I keep looking at my first column, I've gotten 1 0 in there. I want to turn the second one into a 0 as well. I want this to be a 0. So how can I do that? Well, I can note by doing something similar. If I take my row 1 minus 2, row 3 becomes my new row 3, what do I get? My row 1 and row 2 stay the same. It's only row 3 that's changing. Now this is going to say take the number in row 1, subtract twice the number in row 3. That gives me a 0, gives me a minus 1, it gives me minus 1 plus 2, that gives me a 1, and it gives me a minus 2. Now if you don't see how I got that, go through each of the items individually. Okay. So row 1 minus twice row 3, doing each of the numbers individually. Now what does this give me? This gives me my first column with zeros everywhere except for the first number. Now, if I take a look at what to do next. Next, I'm going to look at my second column and say, okay, I have this 5 minus 5 in here in my second one. I want to get rid of the things that are underneath it. So if I do row 2 minus 5 row 3 is my new row 3, what am I going to get? My row 1 stays the same. My row 2 stays the same. Now, Row 2 minus 5 times row 3. Give me a 0. Row 2 has a minus in the second column. I have a minus 5. Minus 5 times minus 1 is a plus 5. That gives me a 0. It's going to give me a minus 10 for the next number. And it's going to give me a 10 for my third number. Now, what do I have here? Take a look at this matrix. This is what is called a triangular matrix. Why is this triangular? I have my diagonal, and everything under that diagonal is a 0. Once I get to this, I'm at a point where I can easily figure out my solution. So I'm going to rewrite that matrix: 2, 1, minus 1, 2, 0, minus 5, minus 5, 0, 0, 0, minus 10, 10. And let's rewrite this as the equations. Turn it back into equations. This was a 2x plus y minus z equals 2. That's just taking this first row, remembering that this is an x, y, z, and constant columns, and rewriting it as an equation. My second row, I have 0 x's, but I have minus 5y minus 5z equals 0. And my third one, oops, that's not minus 1, that's minus 10. I have minus 10z equals 10. Well, this gives me an easy one. Z equals negative 1. Now that I have this one, I can plug it into my second equation. Minus 5y minus 5. Z is minus 1 equals 0. So this tells me that minus 5y plus 5 equals 0, or y is equal to 1. And finally, I can plug this into my first equation. 2x plus, well, y is equal to 1 minus z is equal to negative 1. It gives me 2x plus, and that equals 2. 2x plus 2 equals 2. Or solve this out, I get that x equals 0. So my solution is x equals 0, y equals 1, z equals negative 1. Put this back in the equations, make sure it's correct, but this gives me my solution by using elementary row operations to solve the augmented matrix and turn it into a triangular form. So here's another example. This is a simpler one. Take this and put it into the augmented matrix. We get 3, 6, 2, 4, and 5, 8, like that. There is our augmented matrix. So now let's try to solve this. Here's my matrix. I am going to do the same idea. If I take a row operation of 2 times row 1 minus row 2 gives me row 2. So I'm going to replace row 2 with something new. I get 3, 2, and 5. But my row 2, I get 0. 2 times 2 minus 4 gives me 0. 2 times 5 minus 8 gives me 2. And I've got a problem here. Because remember, this is my x, this is my y, this is my constant. So let's write this out. What do I have? I have 3x plus 2y equals 5. My second row tells me that 0x plus 0y equals 2. Uh-oh. That means that 0 equals 2. That is a problem, because we know that 0 is not equal to 2. This is an example of a system of linear equations that has no solution or is inconsistent. My matrix, when I apply elementary row operations, will tell me after I get to a certain point that there is no solution. And what am I looking for? When I hit a matrix with a row where I have all zeros except for the constant. And if that's a non-zero, but I have all zeros ahead of it, that means I'm getting something like what I have here, 0 equals 2. That's a problem. That tells me that it's inconsistent. So doing the elementary row operations will tell me if it's consistent. If it's consistent, it will give me a solution. If I end up with a row where I have all zeros except for the constant after doing elementary row operations, that tells me it's inconsistent.